Welcome to This Explainer. Today, we're diving into a genuinely fascinating piece of educational history. We're looking at a 19th century Russian textbook that completely rethinks how we learn the absolute fundamental language of mathematics. The book is called Arithmetic by Alexander Malinin and Konstantin Varenin. It was recently translated into English, and honestly, it's not just a textbook, it's a literal masterclass in logic.
Think about it for a second. We all know how to add and subtract, right? We were taught the mechanical steps as kids. But when was the last time you actually asked why you carry the one? Or, why you add from right to left? What if you had to relearn math from the ground up, focusing on the hidden machinery instead of just blindly memorizing the rules? Well, that's exactly the journey we're going on today.
Section 1, A Foundation of Understanding. Let's explore the philosophical shift this 150-year-old textbook brings to our modern, calculator-reliant minds. As the translator of this edition, Valerie Monakin, beautifully notes, Malinin and Burenin's classic text doesn't just hand you a rule to memorize. No way. It explains, step by step, why each rule absolutely must hold. It builds every single idea, starting from the very concept of what a number actually is, all the way to complex multi-digit operations, with this really incredible, unhurried patience. It's all about the reasoning, not just rushing to the final answer. Section 2, The Concepts of Numbers. Before we can even begin to calculate, we have to define our reality. What exactly is a unit, and what is a number? The book brilliantly distinguishes right out of the gate between abstract quantities and concrete realities. An abstract number is just a quantity with no name attached, like just the number 7. But a concrete number, that represents something tangible. It's counting exactly 4 loaves of bread or 5 pens. Or, as they beautifully put it in the book, 7 oscillations of a pendulum. Mathematics essentially acts as the bridge between that abstract concept and the concrete physical world. Section 3, Beyond the Decimal System. Once we have defined our units, we need a way to group them and write them down. And that leads us to the fascinating matrix of numeration. It's absolutely fascinating to break down the sheer efficiency of our base 10 decimal system. We completely take it for granted. The text highlights this incredible underlying logic. 10 units of one order make a unit of the next order. 3 orders make up one class, like units, thousands, or millions. But the most staggering takeaway here, by using this highly structured class and order system, you only need 15 distinct words to fluently name absolutely any number up to 1 trillion. That is just the beautiful economy of mathematical language right there. But the authors don't stop at base 10. To really truly understand numeration, you have to look outside of it. For example, if we used a quinary or base 5 system where each place value represents a power of 5, we'd only have the digits 0 through 4. So the number 5 would actually be written as 10. 24 becomes 44. And a bigger number, like 2,783 in our decimal system, that transforms into a mind-bending 42,113 in base 5. Understanding this really proves that our decimal system is just one specific framework of logic among many possible ones. And hey, it hasn't always been Arabic numerals either. Long before the digits we use today, our ancestors used alphabet-based systems. Take a look at these historical Slavonic numerals. Basically, each unit, 10, and 100 was represented by a specific Cyrillic letter. To show it was a number and not just a word, they placed a special sign called a titlo right over the letter. They even had special symbols to denote thousands. Just imagine trying to do long division with these things. It'd be like a giant puzzle. Section 4. The logic of operations. Now that we know how to define and write numbers, let's break down the hidden logic behind how we actually combine them. The text grounds addition not in some abstract theory, but in concrete, everyday 19th century reality. Addition is simply defined as the successive addition of units. The book poses these very practical problems, like finding out how much money you started with if you spent 35 kopecks on a book and had 55 kopecks left. You just take the units from the second number and literally count them, one by one, onto the first. So here is a really crucial point. Why do we add multi-digit numbers from right to left? It's actually not just some arbitrary rule handed down by strict math teachers. Think about it. If you start from the left and a subsequent column on the right sums to more than 9, well, you'd have to go back, cross out the digit you just wrote, and increase it by 1. We move right to left strictly to avoid constantly crossing out and fixing our digits. We simply keep the extra tens in mind and seamlessly pass them to the next column. It's a brilliant algorithm designed purely for human efficiency.
But mistakes happen. Because human error is pretty much inevitable, the authors don't just teach you how to do the math, they teach you how to definitively prove you're right. They outline these very mechanical processes for verification. If you added top to bottom, check your work by adding bottom to top. Or you can temporarily strike out one addend, sum the rest, and then append the struck out number back to the new sum. It teaches students a rigorous self-verification process, which is honestly a bit of a lost art in the age of just hitting equals on a keypad.
Similarly, they explain the precise underlying mechanics of borrowing and subtraction. Say you're subtracting 5,496 from 12,053. When you hit a 0 in the top number, you obviously can't borrow from it. The authors meticulously break down how you structurally reach all the way over to the thousands place, borrow 1,000, convert it into 10 hundreds, leave 9 hundreds behind, and carry 10 tens to the next column. You aren't just blindly shifting a little number 1 around on the page, you are dynamically deconstructing 1,000 into hundreds and tens to make the subtraction physically possible.
Section 5. Simplifying complex calculations. Finally, let's explore how this deep structural understanding unlocks some absolute math magic tricks. The authors demonstrate how to map out complex, multi-step realities using parentheses. Imagine a super convoluted series of 19th century mercantile transactions involving our shins of cloth or funts of goods. By using simple parentheses, square brackets, and braces, you can visually map out a massive chain of transactions down to a single, highly organized logical equation. It shows the order of operations not as a rigid rule, but as a literal map of real-world events. But what I find truly fascinating, and quite frankly a real lost art in this book, is the concept of the arithmetic complement. It is defined very simply as the difference between a number and one of the next higher order, basically the next perfect power of 10. So the arithmetic complement of 36 is just 100 minus 36, which is 64. And to find it quickly for any number, you just subtract all the digits from 9 except the very last one, which you subtract from 10. But you might be wondering, why does this actually matter?
It matters because of this miraculous little trick. The arithmetic complement allows you to completely bypass difficult, messy borrowing. You can transform a nasty subtraction problem into a beautifully simple addition problem. Take 112,436 minus 57,268. Instead of borrowing across all those digits, you isolate the 100,000, which is that next perfect power of 10, subtract the 57,268 from that to get the complement, and then just add it to the remaining 12,436. By swapping out a string of messy subtractions for their arithmetic complements, you can breeze through complex computations with striking speed to find your final answer. In this case, 56,304. Honestly, it's a real game changer. It shows that math isn't this rigid, unbreakable thing. If you understand the underlying structure, you can actually mold the problem to make it much easier for your brain to process. Which leaves us with a rather provocative thought to end this explainer. Look at the structured, profound, ground-up understanding of logic that 19th century students were mastering. In an age where we are just handed the algorithms, where we blindly memorize rules, and where we rely pretty much entirely on digital screens to do the heavy lifting, have we lost touch with the beautiful language of logic itself? Understanding how to calculate is useful, sure, but understanding why? That is true power. Thanks so much for joining me, and keep questioning the rules.